Hello dear students, my name is Pankaj Sinsinwar and welcome to my channel Maths with Pankaj sir. This is session 2 of complex numbers, so we will be continuing that, and in this lecture we are going to understand how we can represent complex numbers on a plane and basic algebraic operations on complex numbers. So without wasting any time, let's continue the topic. So far we have learned that a complex number can be represented using a plus iota b. So any complex number z can be written as a plus iota b, where a is real part of the complex number and b is imaginary part of the complex number. If you see somewhere that z equals to a comma b, so you have to understand that this is coordinate of a point where x coordinate is representing real part of the complex number and y coordinate is representing imaginary part of the complex number. And we have also studied integral powers of iota, where I is root of -1. So we have understood few properties of iota, like iota raised to 4k is always 1, and from n equals to 1 to 4k, if iota raised to n is asked, then it is always 0. So we can say sum of 4 consecutive powers of iota is always 0. So these were properties of iota that we studied and applied in few questions. So now our objective in this session 2 of complex numbers, is if we have to plot this complex number a plus iota b on a plane, then can we represent this on a real plane where x and y are real axes? So answer is simply no. So we cannot represent a complex number on a real plane. We need to have a different plane. So the plane on which a complex number is represented is known as eigenplane. Fine. So a plane on which a complex number is represented is known as eigenplane. This is, you need to remember. So the next question that comes to your mind is, what is an eigenplane? So now let us understand what a eigenplane is. So if I have to define, a eigenplane is a plane where x-axis is a real axis and y-axis is imaginary axis. Y-axis is imaginary axis. So one thing is clear, that if I have a complex number which is a plus iota b, so this real part of this complex number will be represented on x-axis of the eigenplane, and b, the imaginary part of z, will be represented on y-axis of eigenplane. See, in this question, a complex number 3 plus 4 iota has been represented. So first of all, the complex number on eigenplane is represented by a point. So you can see this point. I will encircle it with red pen. This circle, this is representing complex number 3 plus 4 iota. So this point is representing 3 plus 4 iota. So if I have to plot 3 plus 4 iota on a plane, I will simply plot a point 3 comma 4 on the eigenplane. 3 comma 4. See, you also need to understand that I can also represent this complex number 3 plus 4 iota by connecting that particular point to the origin. So this has already been done by a yellow line. This point 3 plus 4 iota has been connected to origin by a yellow line. So I can represent a complex number by a line which is a connection of the particular point to the origin, or simply a point. I can denote the complex number with a point as well as by a line. So from origin to the point. So now I can say that I can represent a complex number on an Argand plane using a point as well as a line segment connecting point to origin. But when I draw the line segment, I can see that this line segment has some length, or you can say it has a magnitude. So it has magnitude, and when I draw the angle, when I find this angle of the line segment with the positive y-axis and take it as theta, then I can say this line segment also has direction. So I can say that a particular complex number, when represented by a line segment, has a direction as well as magnitude. So in some cases, the complex number follows vector properties as well. For example, a complex number follows triangular law of vector addition as well as parallelogram law of vector addition. So for that, first of all, we need to understand, we need to have a basic knowledge of vectors, that if we have two vectors a and b, so what is a triangular law of vector addition and what is parallelogram law of vector addition? So we will try to understand these two, and then we will go again to complex numbers and we will try to understand that how we can apply it to complex numbers, how we can apply triangular law of vector addition to a complex number or parallelogram law of vector addition to complex numbers. So to understand how complex numbers act as a vector, first of all, we need to understand basic properties of vectors. So we will try to understand two properties of vectors, which is a triangular law of vector addition and parallelogram law of vector addition. So first, triangular law of vector addition. So this triangular law of vector addition says if we have two vectors and two sides of a triangle are represented by two vectors taken in order. For example, these two vectors are connected from head to tail. For example, I have two vectors. This is a vector A, and this is known as this is tail of vector A, and this is head of vector A, and we have another vector B, and if we connect the tail of vector B with the head of vector A, and this is head, and it becomes, these becomes two sides of a triangle, then their vector addition or vector sum is represented by the third side of the triangle taken in opposite direction. So this third side of the triangle, this is the vector sum of A and B. So I will write it as A plus B, vector A plus B. See, we will understand each and everything in detail because the geometrical representation of vector will be very important to you to go into depth and to understand the topic to its best. So these are basics that you need to understand, you need to remember. Second is a parallelogram law of vector addition. Parallelogram law of vector addition. So this parallelogram law of vector addition says that if two adjacent sides of a parallelogram are represented by the vectors, then the diagonal of the parallelogram starting from the point of contact of the two vectors represents the resultant of the vectors or the vector sum of the vectors. So let me draw a clear picture of this. Here you have two vectors. This is vector A, and let me draw vector B. This is vector B, and it does not look like a parallelogram. So anyways, if I draw this is vector B, this is vector A. So the diagonal of this parallelogram starting from this is point of contact. So starting from the point of contact represents the vector sum or the resultant of the two vectors, which is A plus B. So in conclusion, I will say, if we have to find the vector sum of two vectors, we have two methods. One is triangular law of vector addition. Second is parallelogram law of vector addition. So similarly, I can say that complex numbers also follows triangular law of vector addition and parallelogram law of vector addition. This is you need to remember. We will see this in detail in the next slide. This is something you have to note. So now we are moving to the next topic, which is algebra of complex numbers. We will understand addition of two complex numbers, subtraction of two complex numbers, and application of vectors into complex numbers. So then we will see multiplication of complex number, division of complex number, and multiplicative inverse of a complex number. So let us start that how we can add two complex numbers. See, before understanding addition of two complex numbers, we need to understand equality of complex numbers. For example, we have two complex numbers, z1 equals to x1 plus iota y 1 and z2 equals to x2 plus iota y2. And if it is given that z1 is equal to z2, which means x1 plus iota y1 is equal to x2 plus iota y2. So it is obvious that we will compare real part with the real part of the other complex number and the imaginary part of one complex number to the imaginary part of the other complex numbers. This indirectly means that x1 is equal to x2 and y1 is equal to y2. Now if I have to add these two vectors, it becomes x1 plus iota y1 x2 plus iota y2. So I will add the real part of the first complex number to the real part of the second complex number, which will give me x1 plus x2, and taking iota as common, I have y1 plus y2. This is my resultant or the vector complex resultant complex number. If you have to write real part of z1 plus z2, then it is x1 plus x2 imaginary part of z1 plus z2 is y1 plus y2. So I can write it as real part of z1 plus real part of z2, imaginary part of z1 plus imaginary part of z2. From the diagram as well, you can see that you have z1 x1 plus iota y, you have z2 x2 plus iota y2. So using a parallelogram law of vector addition, the resultant is represented by the diagonal starting from the contact or the point of contact of two complex numbers, which are represented by a line joining the point to the origin. So this diagonal is z1 plus z2. Let us now understand subtraction of a complex number. Let z1 equals to x1 plus iota y1 z2 equals to x2 plus iota y2. If you have to find z2 minus z1, so I will subtract the real part of the first complex number from the real part of the second complex number. Okay, wait. So this can be written as x2 plus iota y2 minus x1 plus iota y1. I will subtract the real part of the first complex number from the real part of the second complex number, x2 minus x1 plus iota y2 minus y1. So if someone asks you what is real part of z2 minus z1, so you will say x2 minus x1, and imaginary part of z2 minus z1 is y2 minus y1. I can also write real part of z2 minus z1 is real of real part of z2, real z2 minus real z1. Here imaginary z2 minus imaginary z1. So if you have to represent this subtraction of complex numbers on Argand plane, so we can draw it like this. Let's say this is Argand plane. You have two complex numbers. This is z1 and this is z2. So if you have to find look, try to understand. If I extend z1 z2 on the opposite side of the origin, so those will represent, okay, let me draw it. If I extend z1 on the opposite side of origin, this is minus z1. Similarly, if I extend z2 on the opposite side of the origin, this is minus z2. So using parallelogram law of vector addition, we can simply say using parallelogram law, this will be resultant of z2 and minus z1. We have to represent z2 minus z1 on Argand plane. I can write this as z2 minus z2 plus minus z1. So z2 minus z1 is nothing but resultant vector of z2 and minus z1. So I have minus z1 and z2 as well. So I will find the resultant of these two. This is the line represented by the red color is z2 minus z1. This line will be z1 minus z2. This is real axis and this is imaginary. And if I have to explain addition and subtraction of complex numbers on a single plane, so let's move to the next slide. Let's say this is a Argand plane. And this is z1, this is z2. Okay, so this is z1, this is z2. Real axis, imaginary axis, and if we draw a parallelogram, then it would be so if I connect these 2 points, Okay, so let's say origin is O, this is A, B, C. Z1 is OA, Z2 is OC. So clearly OB represents Z1 plus Z2, and AC represents Z2 minus Z1. CA represents Z1 minus Z2. So I can make a conclusion from here, important, that is going to be used in solving problems, advanced problems, and that conclusion is Z1 minus Z2 is a vector starting from Z2 to Z1. And vice versa. And one more thing is also clear, that if I draw complex numbers as vectors on arcane plane, then using parallelogram law, one of the diagonal represents the vector addition of the two complex numbers, and the other diagonal represents the subtraction of the two complex numbers. So let's now move to multiplication of the complex numbers. Half an hour has already passed, and I had never thought that algebra of complex numbers would last so long. So yes, multiplication. Z1 is again x1 plus iota y1, z2 is x2 plus iota y2. Z1 z2 is x1 plus iota y1. If you multiply x1 with x1 x2 plus iota x1 y2 plus y1 x2 plus iota square y1 y2. We know iota square is a -1, so I will directly write x1 x2 minus y1 y2 plus, taking iota is common, I can write x1 y2 plus y1 x2. Therefore the real part of z1 z2 is x1 x2 minus y1 y2. x1 y2 plus y1 x2. Now the next topic is the division of complex numbers. So whenever we have to divide two complex numbers, we solve it by rationalization, that we have already studied in session 1. So now let's move to multiplicative inverse of a complex number. Let's say we have a complex number. Let me give you an example. 3 plus 2 iota. So multiplicative inverse of z is denoted by z inverse, which means 1 upon z. So I can write this implies z inverse equals to 1 upon 3 plus 2 iota. And further, if I rationalize this, z inverse is 3 minus 2 iota upon 3 minus 2 iota, which gives us 3 minus 2 iota divided by a square minus b square, which is 9 minus b square is 4 iota square, and finally which gives us 3 minus 2 iota upon 9 plus 4, 13. So this is Z inverse, which is known as multiplicative inverse of complex number. Now let us solve some questions, and then we will end this session. Okay, so read this question. It is given x minus 3 upon 3 plus iota plus y minus 3 upon 3 minus iota is iota. If I take LCM, then this can be written 3 plus iota. Try to solve this by yourself, and I will write x minus 3 into 3 minus iota plus y minus 3 into 3 plus iota, which is equal to iota. That is given. This value I know, a plus b into a minus b is a square minus b square, which is 9 minus iota square, 9 minus minus 1, which is 10. So further I can write x minus 3 minus iota plus y minus 3 plus iota equals to 10 iota. If I further expand this, so it becomes, so if you expand this, it gives us x into 3 is 3x, x into minus iota is minus iota x, minus 3 into 3 is minus 9, minus 3 into minus iota is plus 3 iota. And now if we have to expand this, y into 3 is 3y, y into iota is iota y, minus 3 is minus 9, minus 3 plus iota is minus 3 iota, which is equal to 10 iota. Now taking all the iota terms together and remaining terms as one, so we can rearrange 3x minus 9 plus 3y minus 9. I have taken iota common, so I am with minus x plus 3 plus y minus 3 equals to 10 iota. This 3 cancels out, and now I have 3x plus 3y minus 18 and iota y minus x equals to 10 iota. You can see that real part on the right hand side of the equality, real part is 0. On the right hand side of the equality, real part is 0. It means on the left hand side as well, the real part must be 0. So I can write 3x plus 3y minus 18, this must be equal to 0. Also, imaginary part is on the right hand side is 10, and imaginary part on the left hand side is y minus x. So I will write y minus x is nothing but 10. Taking this as equation 1, taking this as equation 2, and solving them simultaneously, I'll get 3x plus 3 of y. Y is 10 plus x from equation 2 minus 18 equals to 0, which gives us 3x plus 3x, 6x, 3 times 30, and 30 minus 18 is plus 12 equals to 0, and x equals to minus 2. On substituting y equals to 10 plus x, we get, so final answer x is minus 2 and y is 8. Let's move to the next question. So read this question. In this question we have to find the least possible integral value of n for which 1 minus iota upon 1 plus iota raised to n is purely imaginary with the positive imaginary part. So first of all we have to simplify this 1 minus iota upon 1 plus iota. So upon rationalization, this becomes 1 minus iota, 1 plus iota, and we will multiply this with the conjugate of the denominator, which is 1 minus iota only. So in the numerator I have 1 minus iota square, and in the denominator I have a square minus b square, so which becomes 1 minus iota square. So I have, if I expand this 1 minus iota square in the numerator, I have 1 plus iota square, so iota square is minus 1, minus 2ab, so which is 2 iota only, and in the denominator I have 2. So I have 1 minus 1 cancels out, so I have minus 2 iota upon 2, which is minus iota only. So we have to find the least positive integral value, so least positive integral for which this is purely imaginary. So basically I have minus iota raised to n, and I have to say least positive integral value. So for this is positive, for this to be imaginary. So for n equals to 0, I have 1. For n equals to 1, I have minus iota raised to 1, which is minus 1 only, and for n equals to 2, minus iota square, which becomes minus 1, minus iota square is iota square only, which is minus 1. So for now, for n equals to 3, I have minus iota raised to 3, which is minus iota cube, and which is minus iota square into iota. You can split this for understanding. Iota square is minus 1, so minus minus becomes plus, and this is iota. So the least value, integral value, which is positive for n, for which this whole expression gives us imaginary value, is n equals to 3. So for n equals to 3, we are getting iota. We are getting iota, which is imaginary. For other values of n, for example, for n equals to 0, we are getting 1. N equals to 1, we are getting minus 1. And n equals to 2, we are getting again minus 1. So for 0, 1, 2, we are getting real values. But for n equals to 3, we are getting imaginary value. That was our question. So let's move to next question. Read this example. If it is given a plus iota b raised to 5 is p plus iota q, this implies a minus iota b raised to 5 is equivalent to p minus iota q. And this conclusion that I have got is very easy to understand from binomial expansion. If you have basic knowledge about binomial expansion, then it will be very easy for you to understand that this expansion will be p minus iota q, because only the term having I will become negative, and the even power terms of b will not get affected because they are in they have even power, and minus 1 raised to any even power is always 1, so that will not be affected. So using basic knowledge of binomial expansion, we will not go into detail of binomial expansion because that will itself take more than 10 minutes. So I have explained to you that how we got this, and then we will move to the next step. And now this equation can also be written as minus iota square. Minus iota square is 1, so a minus iota b. See, minus of iota square is minus of minus 1, which is 1 only. So that will not make any difference, but yeah, it will prove whatever we have to prove in this question. And again, if I write minus of iota square, which is 1 only, 1 into p and minus iota q. And if I take iota common out of this, now I have iota raised to 5, and in the bracket I will be left with minus iota a minus b and raised to 5. Also, if I take iota common here. So I have iota minus iota p minus q. So I can cancel out iota. See, iota raised to 5 is also iota. Iota raised to 4 into iota, and we know iota raised to 4 is 1. So I have iota only. Iota 5 is iota. So I have cancelled out. So if I take minus 1 common, so if we take minus 1 common from this equation, so this becomes minus 1 raised to 5, and in the inside we are left with the b plus a iota raised to 5, and on the right hand side as well, if I take minus 1 common, I have a q plus ip. So this cancels out, and I can write b plus a iota raised to 5 is q plus ip. So this is the important property that you have to remember. So now let's move to next question. Read this question. If the multiplicative inverse of a complex number is root 3 plus 4 iota upon 19, then find the complex number. Let the complex number be z. We know that multiplicative inverse of this number, let z be the complex number, and multiplicative inverse of this number is 1 upon z. So we have to find z inverse, not z inverse, it is given, the multiplicative inverse of the complex number is already given as root 3 plus 4 iota upon 19. So which is basically equal to 1 upon z. We have to find the complex number z. Therefore z equals to 19 upon root 3 plus 4 iota. On rationalizing, we have to multiply and divide by root 3 minus 4 iota, and our numerator becomes 19 into root 3 minus 4 iota upon a square minus b square. So a square is root 3 square, which is 3, minus b square is 4 iota whole square, so it becomes 16 iota square. Iota square is minus 1, so 3 plus 16 becomes 19. So I have 19 into root 3 minus 4 iota upon 19. 19 cancels out, so I am left with root 3 minus 4 iota. So the complex number z is root 3 minus 4 iota. So dear students, algebra of complex number has been completed. I hope you understood the concepts well, and practice as many questions as possible for more clarity, and we will be continuing the same in the next upcoming lectures. Okay, then see you in the next lecture. Thank you so much.